Hello everyone, I am Jainil Patel. I completed my undergraduate studies from IIT Roorkee and today I am going to talk about KRAKENGUARD. So a work done with my co-authors under the guidance of Professor Marios at Imperial College. So KRAKENGUARD is a load time eBPF policy enforcer that provides fine-grained isolation with zero runtime overhead. So let's talk about eBPF programs first. eBPF is a safe in-kernel virtual machine that allows user-defined program to run inside the operating system kernel. The programs are loaded at runtime and they are attached to different kernel hooks based on their types and functionality. Once attached, they can observe and influence the system-wide behavior, like they can read and edit the network traffic, they can trace user space processes, etc. In order to ensure safety, eBPF uses in-kernel verifier that checks programs for memory safety and guaranteed termination. eBPF is no longer a niche kernel feature, but now it runs in production at hyperscalers. Systems like Adrien and Cloudflare's Unimog rely on the in-kernel eBPF programs for real data plane functionalities. The use of eBPF program has also increased in shared environments, like where different untrusted users share the same compute resources in an isolated manner. The usage has increased among cloud developers, and this has also led to growth of projects like Cilium, CubeArmor, Pixie, etc. The most common ways to use eBPF programs in shared environments is mainly through containers and Kubernetes pods. Some solutions also rely on host-level agents to load and manage the eBPF programs. Increasing demand of such use cases have led to development of frameworks like BPFman and Meta's NetEdit. They make lifecycle management, deployment, and orchestration of eBPF programs easier. Considering that eBPF programs are very powerful, BPFman tries to limit the user's ability to load a specific type of eBPF program based on their permission. For example, a user might be allowed to use and load a XDP program, but might be prohibited from using a kprobe. Today, eBPF programs are exposed through broad Linux capabilities, such as cap-BPF, cap-perfmon, or historically cap-sysadmin. Once a process has these permissions, it gets access to all the helpers, maps, and basically the ability to load all kind of eBPF programs. So same privileges are also needed in shared environments. We need to create containers and Kubernetes pods with those privileges. Also, the host level managers requires this permission. The problem related to eBPF and use of eBPF in multi-tenant environment is far from being solved. Some of the problems are as follows. Number one is broader privileges in containers and pod can actually be exploited by the user. The loaded program can interfere with the functionality of other programs adversely. Also, the current solutions for isolation can lead to performance loss, and in some rare cases, the verifier may also fail to provide security guarantees. So now let's talk about these problems in detail. Broader privileges is not built for shared environment and can lead to security vulnerabilities. For example, a container with eBPF privileges can attach a tracing program, which can in turn target a privileged host process. It can then inject malicious payload into that process using offensive helper functions like BPF probe write user, and then try to escape the container by executing desired commands. This is a real-world attack as demonstrated in the given CV. The important point is that this does not require any verifier bug. The current permission model already exposes enough capabilities to make these attacks possible. Next is lack of isolation among eBPF programs. Loading the eBPF program through privileged host service can help us restrict the user from loading certain type of program, but it cannot constrain the program behavior. The loaded program can intentionally or unintentionally interfere with other programs, and this problem could be solved for some selected kind of programs like XDP. For example, we can load the XDP program on the container's virtual interface in order to ensure that it only receives the traffic that is desired for that particular container. But such technique provide isolation, but they limit us from using XDP's ability of processing ingress packet before the network kernel stack. So in this case, the incoming packet first has to traverse the host network stack before reaching the virtual interface. And in our experiment, we compared throughput between UDP echo server. One was like loaded on the host interface, and second one was loaded on the virtual interface. And we found later greater than 40% throughput loss. Also, in some rare cases, our assumption that the verifier always blocks malicious programs is incorrect. There often exists bugs in the verifier that can break the security barrier. Many such bugs that can lead to out-of-bound read and write access in the kernel, leading to privilege escalation, have already been exploited in the past. And some examples of them are shown here. So existing approaches do not provide full fine-grained isolation. They either provide very coarse-grained permission, which is already a poor fit, or runtime enforcement that lead to performance overhead, requires kernel changes and is sometimes partially scoped. There also exist solutions that enforce policy at load time, but they lack stronger guarantees due to the approximate analysis method that they use. And hence, there is a strong need for fine-grained load time isolation, which can be achieved with low or zero runtime overhead. In order to address this, we need to constrain what a eBPF program is allowed to do. We need to be able to check these constraints exhaustively at load time in order to ensure zero runtime overhead. And finally, we need to allow safe collocation without giving up host performance. So let's talk how in general we can constrain a program. So constraining a program means limiting the program's interaction with the system. And in order to provide guarantee over the program behavior, we require the following information. First, we need to know all the possible execution path a particular program can take, and we need to keep track of program's actions on each of these paths. Knowing these preload time can help us ensure constrained execution, and can also help us provide fine-grained isolation. Luckily, in the case of eBPF programs, we have this following two insights. First, that eBPF programs' interaction with the system reduces to 4 interfaces, namely the helpers, maps, memory, and return value. These basically determine what the program can invoke, access, modify, or it can affect in general. And hence, if we constrain this action on every possible execution path, then we can constrain the eBPF program. Second insight brings us to this brings us to an insight that exhaustive symbolic execution on eBPF program can help us provide exact guarantees with zero approximations. In general programs, exhaustive symbolic execution does not provide termination guarantee, can lead from path explosion, and has a very vast surface for analysis. But in case of eBPF programs, the verifier guarantees us termination. There is no unbounded branching, and it has very limited interaction interface, as we discussed in the previous slides. So with this insight, I would like to introduce KRAKENGUARD. KRAKENGUARD is a trusted user space eBPF manager that performs policy-driven checks at load time. It works complementary to the in-kernel verifier. It enables safe delegation, co-location, and can help us provide fine-grained isolation guarantees. It provides a way to constrain the program and also apply conditional policies through symbolic execution. KRAKENGUARD runs as a privileged user space daemon. An unprivileged process sends the eBPF bytecode to it over the socket. It then performs analysis directly on the eBPF object code and does not require the source code. For this, we implemented a lifter that lifts the bytecode to LLVM-IR. KRAKENGUARD then analyzes the program against the supplied policies using symbolic execution. Currently, we use a JSON-based policy language, which could be configured based on the unprivileged user's access levels. If the program is safe with respect to the policy, then KRAKENGUARD loads it into the kernel, otherwise it will reject it. It can restrict which helpers a program may call, which map it may access, and with what permissions, what values a program can return, and which memory ranges it can read or write. KRAKENGUARD can also apply these constraints conditionally based on some previous action taken by the program. The key idea here is that KRAKENGUARD constrains programs' actions and behaviors, not just who is allowed to load which kind of program. So in order to check these policies using symbolic execution, for each program, KRAKENGUARD creates an appropriate symbolic input, for example, a symbolic packet in case of XDP. It then executes the program to explore all the feasible execution paths. Along those paths, it keeps track of program's interaction with the system. Each of those events is checked against the policy during the execution. And if any path violates the policy, then the program is rejected. Now let's talk how KRAKENGUARD performs cross-program analysis to ensure safe collocation. So in order to ensure safe collocation, we need to ensure two conditions. First, the programs do not perform any restricted action, and second, the programs do not interfere with each other in an unexpected manner. The first condition is ensured by single program analysis, as we talked earlier. Now, in order to verify interference, KRAKENGUARD maintains read and write sets per path per program, which basically refers to the map and the memory bytes that each program tries to access. And it then checks how those two programs may overlap. And if there is no unexpected overlap, then the programs can be safely co-located. So now let's move to KRAKENGUARD's policy language. So as I mentioned earlier, KRAKENGUARD uses a JSON-based DSL to define policies. Each policy can have multiple rules, and each rule can have two different types. One is action, and the second is memory condition. Action is basically what the program is allowed to access or what action can it take, and memory condition defines a condition on the memory content. In case of conditional policies, each rule can conditionally depend on another rules based on memory condition or previous action taken. And multiple such conditional could be combined together with logical and or and not operators. So let's talk about an example. In this example, we have two rules here. The first is the check HTTP traffic, which is of type memory condition. And second is process HTTP packet, which has a type action. You can see that it has the first rule in its dependency list. The first rule evaluates true if the incoming packet has a destination port 80, that is, it's an HTTP packet. And if the first rule evaluates to be true, the dependency of the second rule is satisfied. And it is also applied. And hence, constraining read access to the first 54 bytes, while write access from 43rd to the 54th byte, with no access to helpers and maps in the case the incoming packet is a HTTP packet, else this policy does not apply. You can refer to detailed policy syntax in the paper's appendix. So next we move towards the final section of evaluation. Our aim here is to show KRAKENGUARD's feasibility, its evaluation with real-world programs, and its ability to block malicious programs. We will also talk about XDP as a service use case over here. So we evaluated KRAKENGUARD on various real-world programs like Adrien, Electrode, HXDP, Fluvia, various examples from the Linux kernel, and some CVs. Most of them took less than 1 second and less than 100 megabyte of memory. The most time-taking single program we analyzed is Electrode in fast quorum prune mode. And the most complex program pair was Electrode with Adrien. In our results, we also conclude that the cost of the analysis is mainly contributed by the program complexity and not the policy evaluation time, and hence showing the practicality of the solution. The two most prominent real-world program that we evaluated were Electrode and Adrien. So Electrode is a performance acceleration framework that tries to optimize distributed protocols like Paxos using eBPF, while Adrien is Meta's famous open source layer 4 load balancer. For Electrode, we used conditional policies, as it is only allowed to perform actions if the incoming packet has a certain destination port, while for Adrien, we used normal policies to restrict programs access only to the header bytes and no access to the another part of the data. Next, KRAKENGUARD was able to detect and flag the use of offensive helper to modify the program state and was even able to catch other vulnerabilities that exploit the verifier which try to get out-of-bound read and write access to the kernel. At last, we evaluated XDP as a service use case, where we showed how we can attain host-level performance without giving up on isolation guarantees. We verified 2 UDP servers belonging to 2 different services, first on single program policies, and then we performed cross-program analysis to ensure that there is no interference among them. The overall analysis completed well under a second and hence ensuring that the programs were safe to load. Hence, in order to conclude, we identified a problem with the current permission model of eBPF programs and insufficiency of existing solution with respect to multi-tenant environments. We proposed a trusted load time eBPF manager and shown its use with real-world programs. The source code of KRAKENGUARD is open source and available on GitHub. And with this, I conclude my talk and I'm open to any questions.